Okay, so we're going to take a look at determining empirical and molecular formula. So first of all, we've been doing a bunch of formulas, but I've given a couple names. Condensed formula, ball and stick, molecular formula, empirical formula. We have to kind of come to terms with these. So molecular formula is going to contain all of the actual numbers of molecules or atoms that we have. All of the atoms within a molecule. An empirical formula is going to be the simplest whole number ratio of those things. So if we can simplify it, we can. So this is relevant, empirical and molecular, this is all relevant for pretty much exclusively for molecular compounds, nonmetals. Okay, so this doesn't really work all that well for ionic compounds, but here we are. So what's the difference? So here are a bunch of molecular versus empirical. Okay, so give the empirical or molecular formula for the appropriate. So I have a molecular formula of N2O4. Can that be simplified? Yeah, we could say NO2 instead. It's important to recognize that this thing is N2O4, but in terms of like empirically looking at the masses of those two things, those are the same. Okay, so molecular is what it actually is. Empirical is the simplest version of it. C4H10. Yeah, that can be simplified. Divide both by 2. You end up with C2H5. Do these next two. All right. So you should end up with CH2O. And what about sulfuric acid H2SO4? Well, it actually can't be simplified. So in this case, the empirical and molecular are the same. So it's really important. It is okay for empirical or molecular and empirical to be the same. It's okay for those two things to be the same. That's allowed, right? All right, but we can always go from molecular to empirical, even if they're the same, it counts, but we cannot go the other way around. What is the molecular formula of CH2O? Well, we did have this one up here, and that is one of them, but it could be any multiple of that. So it could be C2H4O2, right? It could be C100, H200, O100. So we actually cannot know that. We can't know that at all because that's not allowed. You have to be given information to get the molecular formula. The empirical formula can be pulled. So you can go from molecular to empirical. You can't go the other way around. Right. Good. So let's take a look at some of these, why we need to know these things. So a compound containing 12 grams of carbon and 64 grams of sulfur, find its empirical formula. So these are the types of problems that we're going to need to do, and the concept is pretty simple. I have these two things, carbon and sulfur, and they're in a compound. So I can say if I have carbon and sulfur in a compound, I know I have carbon and I have sulfur, and I just have to figure out those quantities. I should mention that if I have C6, because this is kind of the classic example because this is sugar, these numbers down here are molar quantities. So this is like saying sugar, C6H12O6, has 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen, and that's what makes up the whole molecule. Because it does, when we add them all up, you're adding 6 moles of carbon, you're multiplying that by 6, hydrogen by 12, oxygen by 6, and then adding it all together. So in this example, I know that I've got to solve for X and Y. I've got to determine how many moles of carbon I have and how many moles of sulfur I have. So when we need to convert, we're given gram quantities and we need to convert to molar quantities. Moles of carbon, right? And this one is going to be moles of sulfur. So how do we do it? How do we convert from moles of from grams to moles? That's simple. Whenever we want to go from grams to moles, we're always going to use the molar mass. Molar mass of what? Well, what do we have? I have 12 grams of carbon, and I need to go to moles of carbon. Look at the periodic table. So this is where we're going to convert from one to the other. So I have 1 mole of carbon weighs 12.01 grams. And we know that because it's on the periodic table. So these are supposed to set up to be simple. They're going to get a little more complicated, but the idea remains the same. So we have 12 grams of carbon. We do this math. The units cancel. 12 grams of carbon is equivalent to 1 mole, ish, 1 mole of carbon. Great. So let's do the next one. This was for carbon. We're going to do sulfur next. I have 64 grams of sulfur. I want grams of sulfur to go away. I want moles of sulfur to remain. Look at the periodic table and look at the molecular weight of sulfur. It's about 32. Mass cancel, or the grams cancel, and we're left with 2 moles of sulfur. Great. C1, S1, or C1, S1. C1, S2, or simply CS2. That is our molecular formula. So once we get moles, we plug it in and we're almost there. Okay, so the goal of this is just getting moles in place, and that's kind of where we go. So yeah, so that's how we start. All right. So let's give this one a try. A compound contains 0.16 grams of sulfur and 0.19 grams of fluorine. Find its empirical formula. Again, the only thing that we can get from this is empirical. We don't know if this is actually the molecular formula. Okay, so find the simplest version of this. So I'll give you a chance to try this, and then I'll plug in the answers. So pause me now, give these a try, yeah. So again, same exact idea. These two things together, sulfur X, fluorine Y. By the way, I don't care what letters you use, A, B, F, X, Y, Z. You can use emojis for all I care. It doesn't really matter. 0.16 grams of sulfur times, again, I want to cancel grams of sulfur and turn it into moles of sulfur. 1 mole of sulfur is equivalent to 32 grams of sulfur. Do some math, cancel some units, and you end up with 0.005. In fact, I should go out to sig figs. Ultimately, it's not going to matter because there's quite a bit of rounding involved here. And if there's already been quite a bit of rounding as it is, divided by 32. But yeah, I guess that's going to be 0.005. Oh, technically, moles of sulfur after we cancel units, grams of sulfur. Okay. And the same thing for the fluorine, 0.19 grams of fluorine. Set it up the same way, 19 grams of fluorine on the bottom, 1 mole of fluorine on the top. Units cancel, grams of fluorine cancel, and we're left with 0.010 moles of fluorine. All right, good. So now we plug these numbers in and we're done. So sulfur 0.0050, fluorine 0.010, and we're done, right? Yeah. So we can't have decimals here. So what we need to do is we need to divide by the smallest number that we have there. So if we divide by the smallest number that we have there, 0.0050, and everything by the smallest number we have, life is going to work out for us. S1, F2, or SF2 is what we end up with. Okay. I promise you they can have different formulas than this, but that'll work. Okay. So what we did was we divided by the smallest mole number. Because what that's ultimately going to do is it's going to set one of these, let's use a different color. What that's going to do is it's going to set one of these to 1. And that's exactly what we want to do because we're not allowed to have decimals. So 1 is the maximum or minimum that we can have. Good. So reduce those numbers and take a look at this one. 0.130 grams of sulfur reacted to chlorine to produce 4.28 grams of product. What is the formula here? So I'm going to get you started on this, and then you can go at it. So remember, if I'm reacting sulfur with chlorine, and I'm getting a product, hopefully we only have sulfur and chlorine in there. And if we have 1.30 grams of sulfur plus X amount of chlorine, because it wasn't mentioned, we're going to end up with 4.28 grams of product of sulfur X chlorine Y. Well, they should, because law of conservation of mass says we should be able to calculate this. So now you know how much sulfur you have and chlorine you have, and now do the calculation. Good. All right. What's next? What is the empirical formula of a compound that is 26% oxygen and 74% sodium? So now we are in we're in a new situation where we have a percentage. Okay. So first thing that we did is we convert grams to moles, plug the moles in, and it worked out in our first example. In our second example, we had to divide by the smallest whole number. We had to divide because we had a decimal there instead, and that worked out. So now let's give this a try and let's use percentages. How do we do percentages? Well, there are 3 steps to this. And in fact, it's going to be easy after the first thing. So the first thing that I want you to do is I want you to assume we have 100 grams of product or compound. Because what does that do? If we assume we have 100 grams of compound, that percentage just simply turns into a gram quantity, right? So if I assume I have 100 grams, 26% of 100 grams is 26 grams. Okay, so what that means is for my oxygen, 26.0 grams, 26.0% is actually equal to 26.0% of oxygen is actually equal to 26.0 grams of oxygen, right? And now, in order to get our answer, we're going to convert that to moles. So let's set that up. 1 mole over 16 grams per oxygen. And what you end up with is grams cancel and 1.625 moles of oxygen. Good. All right. Solve for sodium and figure out what the formula is going to be. Okay. All right. So a compound. So now we're going to take a look at what just a little bit more. A compound with a molar mass of 92. So again, all of these up to this point, we're getting empirical formulas. So a molecular formula can only be determined with experimental data. We have to be provided, if we can always solve for the empirical formula, you have to be provided just a little bit more information for the molecular formula. Okay, so a compound with a molar mass of 92 grams per mole. Okay, so we know the molar mass of this thing, so we have a little bit of information. So let's write that. The molar mass of this compound is equal to 92.0 grams per mole. Okay, so we know the molecular formula is going to have a molar mass of 92.0 grams. It contains 0.28 grams of nitrogen, 0.64 grams of oxygen. What is the molecular formula? So what do we have to do? Well, the first thing we can do with these two is we can get the empirical formula. So let's get the empirical formula from this. So really quickly, 0.28 grams of nitrogen, convert that, 14 grams of nitrogen per 1 mole. And you end up with 0.02, 0.02 moles of nitrogen. .02 moles of nitrogen. Perfect. Okay. Charge my iPad before it runs out of power. All right, here we go. 0.02 moles of nitrogen. Okay, and of course, units, grams go away. We're left with moles. Do the same thing for the oxygen. So 0.64 grams of oxygen. You end up with 1 mole of oxygen over 16 grams of oxygen cancel, and we're left with 0.04 moles oxygen. So again, we're going to determine the empirical formula. So I've got N 0.02, O 0.04, divide by the smallest whole number, or smallest number that I have, 0.02, and we end up with NO2. Again, this right here is my empirical formula. So my empirical formula is NO2. And if we figure out what is the molar mass of the empirical formula, the molar mass of NO2, if you do the math, 1 nitrogen and 2 oxygens gives me a molar mass of 46 grams per mole. Okay. So now we're going to use this formula. This formula is going to tell us what multiple we need to multiply our molecular formula by. So we know that our actual molecule weighs 92.0 grams. Okay, so the number of multiples that we need to multiply by. N is equal to the molecular formula weight, 92.0 grams per mole, divided by 46.0 grams per mole. N is equal to 2. What that means is if my empirical formula is NO2, I have to multiply that formula by 2 in order to get my answer. So N2O4 is the empirical, or the molecular. Okay. Again, this data right here has to be provided. Okay. So this one, for example 27, give this a try, is provided for you, right? Good. Okay. All right, combustion analysis. This is the last little bit. I think this is getting a little bit long. So I think we'll probably do the combustion analysis in class. I think that's probably worth doing in class, or I'll create an extra video for it. Actually, you know what? Let's just get it done. So if you want to pause and take a break, that's fine. Combustion analysis shouldn't take too long. It's the same exact concept for the most part, but it's just a little slightly more complicated. All right, so this is how this works. So we have a furnace. We have a little tube furnace that we put a sample in. There's my sample. The sample with a known mass. I know how much mass is there, okay? I am going to put it in with a stream of oxygen gas. So I'm going to run some oxygen gas through this thing. So we're going to heat the sample up. Again, this is a furnace. I'm going to heat it up. And what's going to happen is the sample molecule is going to completely break apart. It's going to atomize. It's going to turn into its individual atoms. So you can imagine atoms of carbon, hydrogen, oxygen, all of those things just popping up. But oxygen is super reactive. So anytime a carbon forms, it forms an oxide. So anytime a carbon forms, and this is actually a pretty decent way of representing it, anytime a carbon forms, some of this oxygen that's present in this furnace is going to react with it, and it's going to form CO2. And anytime hydrogen jumps up into the atmosphere, into the furnace, it is going to react with some of the oxygen and form H2O. And the oxygen molecules are going to double up with each other or with an extra oxygen and form O2. So ultimately what you're going to do is we're going to determine how much water and carbon dioxide we have, and that's going to help us determine what we actually have. So we burn the sample up, we get carbon dioxide and hydrogen, or we get water, okay? So the next thing in line for this is an absorber. So we have this little column, again, it's going to go through here, and this is going to be our CO2 absorber. And we can determine the mass gained of CO2. So we can determine the mass gained by that absorber, and we're going to know how much CO2 was absorbed. And this is going to continue on in a stream, and the next thing in line is going to be a water absorber. And if we know the mass of this thing before and after the trial, we know the mass of water that we've gained. And then it's just going to continue and vent on to something else. Notice that we don't measure the amount of oxygen, but if I know my sample contains carbon, hydrogen, and oxygen, we can always determine the rest was oxygen. Okay. So it's a little bit complicated, but not really. The concept is simple. I'm going to simply take the amount of CO2 and turn that into a moles of carbon. So CO2 gained, grams of CO2, I'm going to convert that into moles of carbon, and I'll show you those conversions. For the water, the grams of water gained is going to be turned into moles of hydrogen. And then everything else is going to be considered oxygen. So everything else, all other mass sample, mass of oxygen. Okay, so let's take a look at a trial for this. So when 2.203 grams of a compound is burned, okay, so it gets burned and it turns into these oxides. 4.401 grams of carbon dioxide is absorbed, 1.802 grams of water are gained, and how much carbon, hydrogen, and oxygen do I have? So what we know is this sample contains those three things. So my compound, carbon, let me use a different color. I don't love red right now. Okay. So carbon X, hydrogen Y, oxygen Z. So I want to solve for X, Y, and Z. I know the mass of the compound is equal to 2.203 grams of the compound. That's the original mass. Okay. All right. So I had 4.401 grams of CO2, and I'm going to do a conversion. Remember when we did the mass percentage, we can use that here. I know that 44 grams per mole of CO2, or really what it is grams of CO2, because it's equivalent to 1 mole, so we don't really need to do grams per mole. So 44 grams of CO2. Notice that that is simply the molecular weight of CO2. Is equivalent to 12 grams of carbon. So think about that for a second. There are 12 grams of carbon and a total 44 grams of CO2. So this is like basically doing percent carbon right here, right in line with the calculation. Grams of CO2 cancels. And now what do we need to do? This is just multiple conversions. Well, at this point, all I need to simply do is say, well, 1 mole of carbon is equivalent to 12 grams of carbon. So grams of carbon cancels. So that first step right here was converting into moles of carbon, or grams of carbon. Now we're going to convert into moles of carbon, and I end up with 0.100 moles of carbon. Great. And that's how we're going to continue. 1.802 grams of water. Again, so we have to think about this. Water weighs 18 grams per mole, or 18 grams of water. Okay. Within that 18 grams of water, I have 2 hydrogens. The hydrogens weigh 2 grams total. Okay, because there's 2 hydrogens, each one weighs 1.0008, right? So 2 grams of hydrogen. That's converting from grams of water into grams of hydrogen. And now we simply do 1 mole of hydrogen is equivalent to 1 gram of hydrogen, because hydrogen is simple. And we end up with 0.200 moles of hydrogen. The last one, oxygen. This one's actually pretty simple in the end. I know how many actually, I skipped the calculations. I went all the way to moles, and I shouldn't have, and there's a reason for it. So if we go back slightly and I do these calculations, okay, so 4.401, so you do this calculation, and I'm going to end up with this unit here, grams of carbon and grams of hydrogen. What do we end up with? I end up with 1.20 grams of carbon, and I end up with 0.200 grams of hydrogen. That's important because I know the total mass of 2.203 grams of my compound minus the 2.0 grams of carbon minus the 0.200 grams of hydrogen. So the hydrogen's taken care of, the carbon has been removed, so that leaves just the oxygen left, meaning my answer is going to give me 0.803 grams of oxygen. And now I can do the conversion. 16 grams of oxygen over 1 mole of oxygen gives me, I just need a little more space and to zoom in so I can write it out, 0.050 moles of oxygen. All right, so I have 0.050 moles of oxygen. I have 0.2 moles of hydrogen, 0.1 moles of carbon, and now I can simply just plug it all in to the equation. So carbon 0.100, hydrogen 0.200, oxygen 0.050, divide by the smallest one, 0.50, 0.050, 0.050, and what do you end up with? We end up with C2H4O. It's a lot, but that's how you do it. So do this next one, combustion analysis for H2O, and I think that's pretty much it. Combustion analysis is about as difficult as it gets. But again, grams to moles, and then as you get to moles, then it's just a matter of kind of figuring it out from there. Okay, that is it. Sorry that one took so long. It's just wanted to walk you through those problems though.